Hello everyone. Today's video is going to be about absolute value functions. We're going to talk about the original parent function, what it looks like, as well as some of the transformations on the parent function, and then some of the characteristics of absolute value functions. So to start off today, we have our original parent function, which is y equals absolute value of x. So if we choose some numbers that we want to plug in for x, when I'm plugging in random numbers, take a look at the graph, I really want to see what 0 looks like. And then I want to pick some negative numbers, say -5. And then I want to see some positive numbers. So I'll go with 1, and then I'll go with +5. So absolute value bars, what's inside those bars always becomes positive. So the absolute value of -5 is +5. The absolute value of -1 is +1. Absolute value of 0 is 0. Absolute value of 1 is 1. Absolute value of 5 is 5. So let's go ahead from here and let's plot some of those values so we get the idea of what the shape looks like for an absolute value function. So I'm plotting -5, 5, -1, 1, 0, 0, 1, 1, 5, 5. So we can see from here that our absolute value function has this V shape to it. So I'm going to just use my straight line tool here so that we can see that we get nice straight lines on both sides. For any value that we plug in for x, we're always going to have this nice straight line, this nice correlation between the x and the y values. So parent function is just y for f of x is equal to absolute value of x. The general form of an absolute value now talks about putting a transformation in there. So y equals a times the absolute value of x minus h plus k. Now in this general form here, again, let's talk transformations. So I'm going to talk about easy one first. This x value here talks about our vertical transformation, talks about shifting our graph up and down. If we have a positive k value, we're going to be going up however many units we're talking. If it is a negative, then we're going down. Again, however many units we are talking. So if this is a +10, then that means we'd be shifting the graph up 10. If it's a -12, then we'd be shifting the graph down 12 units. Switching gears now to the h value. So when I talk about the h value, notice I'm circling just this h here. It's not the sign that's included. And this is what messes up students all the time. We think because we see a minus here that our graph should be going to the left, but it's actually opposite of what you think. So if the h value is greater than 0, then that means we're going to the right. If our h value is less than 0, that means we're going to the left. So we'll do the example down below in a minute, but as of right now, h is greater than 0, we go to the right. If h is less than 0, we head to the left. Again, however many units we're talking. Now the A I saved to last because the A actually has two different jobs. The A tells us whether our graph has a reflection or not. So that piece of the puzzle comes from if the A value is positive. It's greater than 0, then our graph opens up. If our graph is less than 0, our A function is less than 0, then that means that our graph opens down. So our parent function here, our A value is positive. So +1, technically. So that acts almost like slope, which tells us from the origin we can go up 1 and over 1 in both directions. If it was a -1, so if we were going to graph y equals negative absolute value of x, that's that reflection that we're talking about. That -1 is less than 0, so that means our function would open down, and we would actually get something that looks, if it was a straight line, would look like that. So it's just that reflection across the x-axis. Now the A also, like I said, has two jobs to it. The other job is that the A value tells us whether our graph has a vertical stretch or compression. So So a vertical stretch happens when we are increasing more than we are running. If we think about our slope, when our y value is greater than our x value. So if a is greater than 1, it's a vertical stretch. If a is between 0 and 1, it's considered a vertical compression. A is between 0 and 1. It's considered a vertical compression. So the compressions are those wider graphs, and then the stretches are the skinnier, taller graphs. So 4 different transformations that we've talked about. I got 4 different items up here, right? K does one thing, H does one thing, A does 2 things. So make sure we talk about both. If we look down to the example here, take a guess off of these transformations that we just went over. I'll scroll up. So you want to pause the video and then try this yourself. Go ahead. Tell me what are the transformations that occurred from the original parent function. From here, our transformations, we can talk about our -2 value, telling us that our function went down 2 units. Our function went down 2 units. We see that by the -2. Our function went to the left 4 units. We see that because it's opposite of what we think. We would think it would go to the right 4 units because of the +4, but it's opposite. So it's actually going to the left 4 units. And then switching the attention to the A term, we have 2 pieces here. The fact that I see a negative A value means that our graph got reflected across the x-axis. The fact that the A value itself is 1/3 means that that's 1/3 is between 0 and 1. So it's an example of that vertical compression. Okay, so that's a vertical compression by a factor of 1/3. So making sure that when we state our answers for the transformation, that we are being as specific as possible. So it's not just that our graph is going down, left, reflected, and compressed. It's down to left 4, reflected across the x-axis, and vertically compressed by a factor of 1/3. So make sure we have all of those pieces in there. If we switch over now to some of the characteristics of absolute value functions, we need to be able to state the domain, range, x-intercepts, and a whole bunch of different values that we need to be able to answer. So let's talk about our domain. If our domain for all functions right now is everything, -infinity to +infinity. So, right? Because there's literally no number that we can plug in that will not give us an answer. So -infinity to +infinity would be our domain here. Now the range. Range is going to speak to the y values. So for our y values, we need to look at the lowest value and the highest value on our graph. So the lowest value here is at the y value is 0. So we're going to start off with a 0. And that 0 is an included value. It's a coordinate that matches specifically on our graphs. So we're going to put a square bracket around that. If we turn our attention now to the highest y value, well, our y direction is up here, and these arrows are showcasing that our graph just keeps on going in that positive direction forever. And by forever, I mean +infinity. So our range here is just 0 to +infinity. For x-intercepts, we're talking about where our function crosses the x-axis. So our function crosses the x-axis right at this point right here, right? Because this is our x-axis, excuse me. So we know that this point is at, looks like 6. So our x-intercept is going to be at 6, 0. It's important that your x-intercepts are always written as coordinates because that's what they are. Y-intercept, we're looking for where our graph crosses the y-axis. Now for this graph here, it crosses way off our grid. If we continue our pattern, it looks like we're going up 1, 2, 3, and over 1, up 3 and over 1. So if we went up 3 again, we would be going 1, 2, 3, 4 more times. So 3 times 4 is 12. 12 plus 6 is going to give us 18. So it looks like for this function, we'll confirm that in a minute, our y-intercept would be 0, 18. Okay. So you're just looking for where the function crosses the y-axis. If we're speaking to a positive interval is the top part of our graph. We have all positive values above the x-axis. Now our function is entirely in the first and second quadrants, entirely above the x-axis. So that means our positive interval is literally the entire function across its domain. So our positive interval is everything. And when we say everything, that means we're talking about negative infinity all the way to positive infinity. In that case, negative interval, now we're talking below the x-axis. So below the x-axis is anything down here, of which our function doesn't fall there, not at all. So our negative interval here would actually not exist. So I put DNE, does not exist. You could have also put NA, not applicable, anything to that effect, just don't leave it blank. We're talking interval of increase and decrease. So if we look back at our function, we see that we have some decreasing values, and then we have some increasing values. So it looks like we're asked for increase first. So the increasing portion of the graph is here and beyond. So interval of increase and decrease is talking about the x values. So our graph changes from a decreasing function to an increasing function at 6. So 6 is going to be our magic number as we're writing our, as we are writing our interval of increase and decrease. So we are increasing from 6 all the way out to infinity. And always put parentheses around this. Okay, the only time we're going to see brackets come into play is in that domain and range section. Everything else is a parenthesis. Our interval of decrease, then, we talked about is this left side of the graph, which is from negative infinity out to 6. So negative infinity out to 6. And again, parentheses around everything. All right. So that goes through one example, all the different characteristics of our function. So now you try. Pause the video, take a look at the graph that's here, and see if you can state the domain range, x and y intercepts, positive, negative intervals, and intervals of increase and decrease. When you're ready to check your answer, go ahead and hit play. All right, here we go. Domain. Ready? Our domain is going to be, see if you got it, negative infinity to positive infinity. Range is 0 to infinity. X-intercepts are going to be located at 2, 0. Our y-intercepts, make sure you wrote those as coordinates, please. X-intercepts is at 0, 6. This one was an easier problem because it was right on the grid. 0, 6. Our positive interval is, again, this entire function is positive. So negative infinity to positive infinity. Our negative interval then would simply just not exist because there is nothing in that negative region. Our intervals of increase is 2 to infinity, that right side of the graph. And interval of decrease would be negative infinity to 2, the left side of the graph. Well, I hope this video helped to clarify some questions. Have a great day.